Video 65 of the master course Quantum Chemistry of Molecular Electromagnetic Properties. The topic of this lecture is Möller-Blechert perturbation theory. Möller-Blechert perturbation theory is the simplest of the wave function methods to improve on the results of Hartree-Fock theory, which means to include some of the missing electron correlation. Möller-Blechert perturbation theory is the application of perturbation theory as we have developed it in chapter 3 to the problem of electron correlation. Therefore, in the first step, we partition the Hamiltonian, which is the field-free molecular electronic Hamiltonian, in two parts, where we partition it now in the Hartree-Fock Hamiltonian here, which is the sum of the Fock operators for all the electrons, and what is called the fluctuation potential, which is going to be the perturbation. The fluctuation potential itself is just the difference between the correct electron-electron interaction and the averaged electron-electron interaction as it is included in the Fock operators. Like always in perturbation theory, the wave function is then expanded in the perturbation series in orders of this perturbation, which is the so-called fluctuation potential. The name fluctuation potential actually arises from the fact that it's the difference between the correct electron-electron interaction and the average value. So it is the fluctuations around the average value. In the expansion of the wave function, we use the Hartree-Fock determined as our zeroth order wave function, which is consistent with the fact that the Hartree-Fock single determined wave function is an eigenfunction to this Hartree-Fock Hamiltonian. Similarly, like the wave function, we also expand the energy in a perturbation series with a zeroth order term, which is the eigenvalue of the Hartree-Fock determinant with respect to the Hartree-Fock Hamiltonian, which means it's the sum of the orbital energies. Then we have a first order correction, second order correction, and so forth. In order to distinguish between the energy corrections to a given order, like for example the second order energy correction here, and the energy to second order, which means including all the corrections up to including second order, we put a subscript 0 to the sum of the energies up to the given order. Now the Hartree-Fock energy turns out to be actually the sum of the zeroth order energy and the first order energy. The zeroth order energy was just the sum of the orbital energies, so this is not the same as the Hartree-Fock energy. One can easily see that also if one remembers that the HSTF energy is calculated as the expectation value of the full Hamiltonian with the Hartree-Fock wave function. Now the full Hamiltonian here we have right up as the zeroth order Hamiltonian and the first order Hamiltonian, which means our Hartree-Fock Hamiltonian, and the fluctuation potential. And the Hartree-Fock wave function, Hartree-Fock Slater determined, is our zeroth order wave function. Which means that if you look at the first order energy correction, which is the zeroth order wave function with the first order Hamiltonian, so this is just this part of the Hartree-Fock energy, the one with the fluctuation operator, and the zeroth order energy is the part with the Hartree-Fock Hamiltonian, which means that the zeroth order plus the first order energy is the same as the Hartree-Fock energy. That also means if you want to get a correction to the Hartree-Fock energy, we have to go at least to the second order energy correction. So the first correction of Hartree-Fock will be in second order from Möller-Blechert perturbation. Like in general in perturbation theory, we will expand the first order and second order and higher order corrections to the wave function, again in the complete set of the eigenfunctions of the zero order Hamiltonian. And the complete set of eigenfunctions of the zeroth order Hamiltonian is the Hartree-Fock Slater determinant plus all the other determinants which we can generate from the Hartree-Fock orbitals, which mean the singly excited determinants, the doubly excited determinants, and so forth up to the n-tuply excited determinants. If you use then this set of unperturbed wave functions and insert it in the expression for the first order correction to the wave function, we obtain this here. This is essentially just the expression as we had it in chapter 3, but now inserted the operators where we have, because our zeroth order Hamiltonian is the Hartree-Fock Hamiltonian, our first order Hamiltonian is this fluctuation potential. Right, and then the question arises, of course, which excited determinants phi n here can actually contribute. And that's one of the cases where we can now apply our Slater-Condon rules and the Pre-Young theorem. Because the Slater-Condon rules tell us that if this is a 2 and a 1 electron operator like our Hamiltonian, which means the maximum difference between those two determinants can be in 2 spin orbitals. And since this is the Hartree-Fock determinant, these determinants can at most be double excited determinants. And then we can also show that this integral is actually essentially the same as the one with a full Hamiltonian, at least as far as the Pre-Young theorem is concerned. And that means that if phi n would be a single excited determinant, this integral also would be 0, which means the only excited determinants which can be used or can contribute here are doubly excited determinants. And therefore, we can also write this as the application of the double excitation operator T2, which gives us a sum of double excited determinants with some coefficients here, and the coefficients, these T coefficients, which in the case of Miller-Blissett perturbation theory are called correlation coefficients. And since we're looking at the first order wave function, this is the first order doubles correlation coefficients. They are essentially this here. And for a particular set of double excitation operators, it turns out to be these, which means it's just a 2-electron integral divided by the sum of orbital energies. And the sum of orbital energies comes about from here, because here we have our Hartree-Fock Hamiltonian, and the excitation value of this Hamiltonian with the SZF wave function is the sum over all the orbital energies of the occupied orbitals. And this is the corresponding excitation value with a double excited determinant, which means this is the sum of all the orbital energies of the orbitals included in this determinant. And since those two determinants differ by 2 orbitals, there are 2 occupied orbitals from the Hartree-Fock determinant replaced by 2 virtual orbitals. The only thing which remains by subtracting those two sums are precisely the orbital energies of those 4 orbitals which differ. Now, the second order energy correction can then be, like always, be calculated as this asymmetric excitation value, where we have the 0th order wave function, which is our Hartree-Fock determinant. We have the first order operator, which is our fluctuation potential, and then we have the first order correction to the wave function. And the first order correction to the wave function, we know that it was the T2 operator applied to the Hartree-Fock determinant. Inserting these and evaluating the integrals, we get here a sum over a 2-electron integral, and then a particular combination of these first order doubles correlation coefficients. The second order correction to the wave function is again expanded in the set of the unperturbed wave function, which means in the complete set of Slater determinants which we can make from the Hartree-Fock orbitals. And then we get a coefficient which is more complicated as in the first order, but it's precisely that coefficient which we had derived in chapter 3 when we looked at perturbation theory. So we get now different terms here. We get here a matrix element between now the first order correction to the wave function, the fluctuation operator, and the excited determinants. And here we have an overlap between the first order wave function and these excited determinants. Since we're now starting with the first order wave function here, which are double excited determinants, and we have our fluctuation operator, which, as I said, is a sum of 2 electron operators and 1 electron operators, then the determinant here again can differ by at most 2 orbitals, spin orbitals, but since this is double excited, we can actually go down to single excited, we can have double excited, again we can go up to triply excited, and we can go up to quadruply excited, which means the second order correction to the wave function will include single excited determinants, double excited determinants, triply excited determinants, and quadruply excited determinants with different correlation coefficients. Now the coefficients come from here, and one should note one thing is that in the matrix elements up here enter the first order correction to the wave function, which must mean that the coefficient for the second order correction to the wave function will include the correlation coefficients, the first order correlation coefficients. Now I will not go through all of them, but I just illustrate the second order single excitation correlation coefficient, where phi n will be a single excited determinant. The expression for this looks then like this. And you can see, first of all, we have also 1 over an orbital energy difference again, but now it's just the orbital energy difference between one virtual orbital and one occupied orbital, which is a consequence of that we had a single excited determinant, which differs from the Hartree-Fock only by one orbital. And then you can see we get, again, a 2-electron integral, and then multiplied with a combination of first order double correlation coefficient, as I said, because the higher order, the second order correlation coefficients depend on the first order correlation coefficients.